Right, this is Electric Circuits course of second semester students in the Department of Electrical Engineering, UIT Lahore, and I am Dr. Khalid Emerson. Our previous lecture was on node voltage method, and this lecture is on mesh current analysis. The textbook reference is chapter 3, and I hope all students they are aware of the textbook. In mesh current analysis, we use Kirchhoff voltage law, and Kirchhoff voltage law states that sum of the voltages in a loop, sum of all the voltages in a loop of n elements is equal to 0. Now, the mesh current analysis, this method is also known as loop analysis or loop current analysis. Basically, loop is a closed path in a circuit without repeating a node in the circuit, while mesh is also a closed path. The difference between these two is that a mesh is a special type of loop which does not contain another loop inside it. To explain it, I will present a circuit here. This is a simple circuit so that you can understand things quickly. In the following discussion, I will show you more circuits. So we have a node here, we have a node here, we have a node here, and we have a node here. Let us call it voltage source 1, this is voltage source 2, and this resistance is R1, this resistance is R2, and this resistance R3. We will be using R1 of I think it is R1 is 3 ohm, R2 is 9 ohm, and R3 is 6 ohm. We'll use some values, constant values for voltage source 1 and 2 in the following discussion. Now we see how many closed paths in this circuit we have. You see, if we start from here, we go through R3, and then this is a closed path. There is another closed path, R2, the voltage source, and then R3, this is another closed path. Yet there is another closed path. If we start from here, go through this, and then this is another closed path. Now, how many loops and how many meshes in it? If we see the yellow over here, this closed path is a loop as well as a mesh. Another closed path over here, a loop as well as a mesh. Let us call it A and call it B. And there is another closed path over here, the outer side. If we see over here, this is also a closed path. This is a loop. Now, which one is loop and which one is a mesh? Sorry. Here we see that A and B both are meshes and loops as well. But the outer loop over here, this is a loop but not mesh, because it consists of two loops inside A and B. This way, in this circuit, number of loops equal to loop A loop B, and the outer loop. Number of loops equal to 3, and number of meshes is 2. In mesh current analysis, we need equations, mesh equations equal to number of meshes in it. So here we have 2 meshes, therefore we need 2 mesh equations. Now I will write equation for mesh A. In writing equation for a mesh, we start from somewhere and then we make a closed path. We go in this direction. Following the direction of the current flowing through R1, if I reproduce over here R1, and current is flowing in this direction, and the current flowing is IA only, the polarity of the voltage drop across this R1 will be as shown. This is the voltage drop. And then we see R3 over here, R3, and if we move along the direction of mesh current A, which is the downward, we see that through R3, IA is flowing downwards while IB is flowing upward. Basically only one current is flowing downward. These are fictitious currents which we use in our analysis. Here we see what is the net downward current. Net downward current flowing through R3. This is following the directions. IA is flowing downward, IB is flowing upward. So this is the net downward current flowing through this resistance R3. I'm saying downward current because we are following the direction, assumed direction of mesh A. Now equation, if we write equation, the voltage drop across R1 is due to current IA. The voltage drop across R3 is the net downward current here, which is IA minus IB. And if we see mesh A, look at the circuit in the green color over here. So here, if we go through this voltage source, we see negative sign first and positive later. So if we move in this direction, that first terminal is negative, this is known as voltage rise. Because it is a voltage rise, we write it at the right hand side, and this is VS1. You know, this is VS1. So we have considered mesh A and we have written the equation for mesh A. We started from here and then over here closed path. So this was a drop and this was a drop due to the resultant current flowing downward. As R3 is shared by 2 meshes, IA and IB, downward current is IA minus IB, and then this is voltage rise. VS1 is a voltage rise. We can rewrite this equation by over here combining IA terms. So we have R1, we have R3 times IA and IB, only one IB term. So this is minus R3 IB, and the right hand side is VS1. This is our equation 1. And now we will write equation for mesh B. I will reproduce mesh B over here again, leaving the original circuit intact. This is R3. Only mesh B is reproduced over here, and we have assumed that the direction of current flowing in mesh B is clockwise. Note that we have assumed both currents flowing. We have assumed, look at the circuit diagram here, we have assumed the direction of current flowing in both meshes clockwise. Later I will show you that we can select the direction of mesh currents randomly as well, but there is some advantage in assuming all the mesh currents in the same direction, either clockwise or counterclockwise. Now mesh B, start from here, look at the circuit diagram, start from here, only IB is flowing through this, and therefore the voltage drop is with this polarity over here. So this is voltage across R2 only due to current B. Now here we have to consider each circuit element in the mesh. So here we see that the sign of the first side of this voltage source is positive. This is also a voltage drop. Therefore, if we go from positive to negative, it is a voltage drop, and if we go from negative to positive, it is a voltage rise. So this is a voltage drop, so I will write it along with the voltage drops across each element. And then this is R3 over here, following the direction of IB, which is upward over here. But now you should know that IA is flowing in the opposite direction. So what is the net current, net upward current flowing through this side? So as we are in mesh B, therefore the net upward current will be IB minus IA, and it will be a voltage drop because it is positive and negative over here. So this is voltage drop across I3 due to the net current flowing in upward direction. Why upward direction? Because we are writing equation for mesh B, and direction of the mesh B is clockwise. Sorry, I should have written IA over here. Sorry for this. So we have completed the closed path, and there is no element, there is no other element in it. So right hand side is equal to 0. It's a voltage drop, and in this direction voltage drop. So this is our second equation. And now deleting this, we can rewrite this, the second equation, by combining coefficients of IA and IB. This is IA, so this is minus R3IA, and then IB, this is IB and this is IB, so this is plus R2 plus R3 IB. There is another term in it over here, VS2. So if we express to the right hand side, this is VS2, and this is very important. You have to consider the signs of each and everything. And then this is our equation 2 for mesh 2. Now, writing these two equations, equation 1 and equation 2 in matrix form, we see that it is R1 plus R2, and this is coefficient of IA, and then minus R3, this is coefficient of IB, right hand side is VS1. So in matrix equation, we will this matrix equation will be representing two mesh equations over here, and this is over here like that. So we will read this equation as R1 plus R2 IA and minus R3 IB is equal to VS1. Now equation 2. Equation 2 is minus R3 IA and R2 plus R3 IB, and the right hand side is equal to VS2. Considering values of R1, R2, R3 shown above, R1 plus R2 is 9, minus R3 is minus 6, minus R3 again minus 6, and R2 plus R3 is 15. So this is our first matrix. The second matrix in the right hand side is IA, IB. This is also known as current matrix, and the right hand side is the voltage matrix over here. This is VS1 and minus VS2. Be careful about the signs. Now as the matrix over here, 9 minus 6 minus 15, it consists of all resistors, so we can call it R matrix, and IA, IB, we can call it I matrix or current matrix, and the right hand side we can call it voltage matrix. From here we can solve this matrix equation by taking inverse of R matrix and multiplying it by V. So here I will solve it for you over here. So I matrix over here, which is basically IA and IB. So this is inverse of the matrix, inverse of this matrix over here, inverse of this matrix, and you see inverse is 15 and 9 and 6 and 6. I hope you will be able to recall it quickly how to compute the inverse. This is the adjoint divided by determinant, 9 multiplied by 15 and minus 36. So 15 minus 36, this is 99 multiplied by VS1 and minus VS2. Further, if we proceeded further, this will be equal to multiplying. I'm multiplying these two matrices over here, and this is 15 VS1 minus 6 VS2 and divide by 99. We are over here in the denominator, and the second row of this matrix is 6 VS1 minus 9 VS2 divided by 99. Further, we can express it as 15 divided by 99 VS1 minus 6 divided by 99 VS2, and the second element, it is 6 divided by 99 VS1 minus 9 over 99 VS2. Finally, we can write IA. This is first element is IA. Again, I repeat, 15 divided by 99 VS1 minus 6 over 99 VS2, and IB is equal to 6 over 99 VS1 minus 9 over 99 VS2. Now, using values of VS1 equal to, say, VS1 is 12 and VS2 is equal to, say, it is 9 volt, this will be equal to, then if we compute it, it will be equal to 1.2727, and this will be equal to minus 0.0909. So this is the solution. We have found IA and IB. Sorry, I should have written in a separate. Again, this is our IA and this is IB. So we have solved the matrix equation. We have found IA and IB. Now, Reproducing the circuit again. Now I will be using values directly. This is 3 ohm and this is 9 ohm and this was 6 ohm, and the voltage over here, this is 9 volt which I used over here, and the voltage over here, this is 12 volts. As I said earlier, direction of mesh currents is first of all I have to draw it properly, a circle over here. Now previously we assumed the direction of current flowing in mesh A clockwise and direction flowing in mesh B also clockwise. This is not necessary. We can assume any random direction. So I will assume the direction over here counterclockwise deliberately. See what happens. And now write equation for mesh A. Now you see again, starting from here, look at the circuit diagram. Starting from here, what is the voltage drop due to the current IA which is flowing through it? The polarity is shown. This is the voltage drop along with its polarity. What is the net downward current flowing through it? I will repeat. If we write equation for mesh A, we will see the voltage drop in the direction of mesh A, which is due to clockwise, which is downward. So what is the net downward current? Net downward current over here, net downward current through 6 ohm. I'm repeating again and again. So it is IA. But interestingly, previously you see over here in this circuit, the net downward current was IA minus IB. But here the net downward current IA is flowing downward and IB is also flowing downward. So net downward current is IA plus IB. This is the difference. Instead of IA minus IB, it is IA plus IB because we have chosen the opposite direction of mesh B current. Now write equation for mesh A. It is same as the previous because the direction, it is the voltage drop across 3 ohm resistance over here is 3 IA, and the voltage drop across the 6 ohm resistance due to the net current flowing downward is across 6 ohm. IA is flowing downward, IB is also flowing downward, and over here if we go through this, so this is a voltage rise, so we write it at the right hand side, and we can write this equation as 9 IA plus 6 IB is equal to VS1, and this is our equation 1. Now write equation for mesh B. So writing equation for mesh B, we over here. Now I'm writing equation for mesh B. In mesh B, I have to move along the direction of the current flowing in mesh B. So if I start from here, so current is flowing from right to left, and therefore the polarity of the voltage drop across 9 ohm is as shown, and in here I have to move downward over here following the direction of the current of IB. So what is the downward current? Net downward current flowing through 6 ohm. Again, IB is flowing downwards as 6 ohm is shared by mesh A and mesh B. So it has another current IA flowing in the same direction. Therefore, we write equation as voltage drop across 9 ohm due to current IB, and the voltage drop across resistance 6 ohm due to IA and IB. So I am not writing IB minus IA over here because it is due to the assumed direction of currents. So both currents are flowing downward, and if I move around the mesh, I see that the first side, the first sign of the 9 volt source is negative, so it is a voltage rise. So the right hand side, it will appear at the right hand side, and I will write it as okay. I can write the exact value or VS2 as well. Combining coefficients, it is 6IA. I have considered this. Now coefficients of B is 9 and coefficient of B 9 and 6. So it is 15IB. Right hand side is equal to VS2. And I express these two equations. This is equation 2. This is equation 2. I write these two equations in matrix form. Equation 1, which is 9IA and 6IB, and right hand side equal to VS1. Second equation, which is over here, it is a 6IA plus 15IB is equal to VS2 over here. And now IA, current matrix IA IB is equal to inverse of this matrix, which is 15 and 9 and minus 6 and minus 6 over here, and divide by its determinant, which is again 99, multiplied by this matrix. So this is VS1 and this is VS2 over here. So again this is equal to 15 VS1 divide by minus 6 VS2 divide by 99. The second row is minus 6 VS1 plus 9 VS2 divided by 99, and further I can say it is 15 divided by 99 VS1 minus 6 divided by 99 VS2, and the second row is minus 6 divided by 99 VS1 plus 9 divided by 99 VS2. Now IA and IB, considering VS1 is equal to 12 volts and VS2 is equal to 9 volt, this is then 15 divided by 99 multiplied by 12 minus 6 divided by 99 multiplied by 92, and this is minus 6 over 99 VS1, and this is plus 9 over 99 multiplied by VS2, and we see that the voltage is 1.2727 and 0.0909. So from here we see that IA is 1.2727 and IB is 0.0909. Now what is the difference? Previously if you see this, IA is 1.27, IA is 1.27, IB over here is equal to minus IB is equal to, I forgot over here, IB is equal to minus 0.0909 and IB over here is plus 0.0909. So whenever we see the sign, ultimate sign of our current, So the plus means the actual current is flowing in our assumed direction. IB, again positive, the actual current is flowing in our assumed direction. See this, IA, the actual current is flowing in our assumed direction, but this negative sign means that the actual current is flowing opposite to our assumed direction, because in this circuit we have assumed clockwise direction of IB, and in here we have assumed counterclockwise direction of IB. So these directions, both directions are opposite, therefore the signs are opposite, and while IA is same. So it means that you can choose the direction of mesh currents randomly. But there is advantage of writing, of assuming all the currents, all mesh currents in the same direction. There is another aspect of this circuit. Another aspect of this circuit is, I would like to reproduce this over here. If I can move it downward, I reproduce it over here. Right. We have written, as we have number of meshes equal to 2, but number of loops are 3. The third loop, as I mentioned in the beginning of this lecture, the outer loop over here, this is the outer loop, this is third loop. Let us see what happens if we try to write loop equation for this outer loop. You know, we start from here, look at the circuit diagram. If we start from here, from 3 ohm resistance, the current flowing through this 3 ohm resistance is IA only, and the polarity of the voltage drop will be as shown. Now next, because we are considering the outer loop, the direction of the current flowing is from left to right, only IB is flowing through it, so this is the polarity. So the polarity of the voltage of this voltage source is positive and negative. We are following the direction of the loop over here, so it is another drop. Now over here, so if we go through the voltage 12 volts, so this is voltage rise. Now I write equation for the outer loop. So this is 3IA and then plus 9IB only, and this is a voltage drop 9 ohm, and the voltage rise over here, this is the last element in the outer loop, this is equal to 12. And now rewrite this equation. So this is 3IA plus 9IB is equal to 12 minus 9 equal to 3, and again it is 9IB is equal to 3. This is our third equation. How many variables we want to evaluate? Number of variables is equal to 2. How many maximum equations we need? 2. But what about this third equation? You see that previously equation, look at equation 1 and equation 2. So equation 1 and equation 2, if you see over here, this is equation 1, 9IA minus 6IB. So this is equation 1, 9IA minus 6IB is equal to VS1. So this is equal to VS1, and we are assuming VS1 equal to 12. So this was, again I will use the number over here 1, and second equation here, second equation, minus 6IA plus 15IB. So this is minus 6IA plus 15IB, and if you remember it was minus VS2. This is equation number 2. Now interestingly, if we see these two equations and we add these two equations, what we get? If we add these two equations, we see it is a 9IA minus 6, it is a 3IA, and it is 9IB, and this is equal to 3. This is interesting result. Compare this with this. The third equation which we have written due to outer loop, it was an additional equation, but we have seen that the already existing equations, equation 1 and equation 2, these two equations can be added to have this equation 3. So this is an additional equation. This additional equation does not convey additional knowledge to solve mesh equations. So that is why we write number of equations equal to number of meshes, not equal to number of loops, not equal to number of loops. And now this was an additional point I wanted to emphasize over here. So I will leave everything over here. Now, you can solve these two equations graphically, as I have explained in the previous lecture. And solving these two equations graphically, we have two equations, and sorry, this is something went wrong with it. Sorry for that. So this is let this be, this axis representing IA, and this is IA, and this axis representing IB. So we can use equation 1, and we see that IB when IA is equal to 0. So this is what? When IA is equal to 0, this is minus 12 over 6. So this is minus 4 by, sorry, this is minus 2. This is straightforward. This is minus 2. This is minus 2. And here IA is 0. For IA equal to 0, IB is minus 2. Where is this point on this plane? IA is 0 and IB is minus 2. Say we are here. So this is minus 2. IB minus 2 and IA equal to 0. Second thing in it, what is IA in the same equation when IB is equal to, this is a quick method to draw a line. Otherwise we have to use a range of values of IA, and for each value of IA we compute IB and we draw a line. So in this equation again, IA is equal to 12 divided by 9. So 12 divided by 9 is 4 by 3. So 4 by 3 is 133, and if it is 2, and let it be somewhere over here, so this is 4 by 3. IA is 4 by 3. So we have got 2 points on both axes, and we can draw a line over here, and this line represents equation number 1. And now equation 2. In equation 2 over here, this equation 2 over here, what is IB when IA is equal to 0? When IA is equal to 0, IB is minus 9 over 15, and this is equal to minus 3 over 5. So this 3 over 5 is 0.6. So this is minus 0.6. Where is the point in this axis? IB minus 0.6. This is 1. So let it be this. So IB minus 0.6 while IA is equal to 0. What is IA when IB is equal to 0 in the second equation? In the second equation, IA when IB is equal to 0. So this is 9 over 6. So this is 3 by 2. So this is 1.5. So 1.5 maybe here 1.5, and now drawing a line over here, it is if I draw a line, it is this. So this line is representing equation 2. Where is the solution? Solution is the point of intersection over here. This is the solution. This is the solution, and you can verify that in here IA is 1.27 to 1.2727, and IB it was minus 0.09 over here. So it's almost a freehand sketch of IA and IB in a 2D plane. You can sketch it accurately, and in order to find it more clear over here. Now, as I said, the third equation which we wrote, look at over here, the third equation, this was an additional equation which we wrote due to the outer loop. So if we draw a line due to this third equation, this line will not be new to these two lines. So nothing will be added in our previous knowledge. So we write number of equations. We need number of equations is number of equations equal to number of meshes in a circuit. And now I will take another example over here. So this example, I have selected various examples in this lecture, and in this example I have selected examples carefully. This is the current is say I'll be using actual value of the current, and I will keep these circuits simple so that you can understand quickly. This is 8 ohm, and again this is 8 ohm. If you remember, I used the same example in my lecture on node analysis. So you can correlate the results of this using node analysis and mesh current analysis. So in it we see how many number of meshes. So this is mesh A, this is mesh B, and this is mesh C. Again I will repeat. We can assume random directions of all the meshes, but it is better if we choose all clockwise or all counterclockwise. So say we can assume clockwise, we can assume counterclockwise. Say we can assume this the current in mesh C counterclockwise. There will be no difference in our analysis. Now, writing equation for mesh A. In mesh A, it is very clear. When, listen carefully, when a current source is shared by only one mesh. The mesh current is given directly, can be found directly. Only IA is flowing through this current source. So IA is 2 ampere. So this is very simple. So if you can recall, if a voltage source appears between a node and a ground node, there is no need to write equation for the node voltage, because node voltage is given directly as shown by the voltage source. So it is a dual situation in mesh current analysis. So IA is, we know what is IA due to the current source, yes. And now B. We use the same method. We start from here. Look at the circuit diagram. We start from here and see which current is flowing through this. Only IB is flowing through this, and the voltage polarity is as shown. What is the net downward current flowing through this 8 ohm resistance? Net downward current. This is IB minus IC. And what is the net upward current flowing through this 4 ohm resistance? This is IB minus IA, because we are following the direction of the current of mesh B. So the polarity is shown over here. The polarity for this is shown. And now write the voltage drop. This voltage drop, look at the circuit, this voltage drop across 8 ohm resistance due to current IB, and then the voltage drop across this another 8 ohm resistance, which is shared by mesh B and C. So this is plus 8 IB minus IC. IB is flowing downward, IC is flowing upward. Net downward current is IB minus IC. And what is this voltage drop across this 4 ohm resistance? So IB is flowing upward, IA is flowing downward. So the net upward current flowing through 4 ohm resistance is IB minus IA, and there is no voltage source in this mesh. Right hand side is equal to 0. Combining coefficients of IA, IB, IC. This is IA, this is IA, so this is 4IA. And then IB. This is IB, 8IB and 8IB and another IB, 4IB. So this is I forgot the negative sign over here. So plus 8 plus 8 plus 4, it is 20 IB, and then IC. So over here this is minus 8 IC, and the right hand side is equal to 0. Now we can say that this is our equation 1. This is our equation 2. Here C, mesh C. So we are writing equation for mesh C. In mesh C, we start from here. Look at the circuit diagram. We start from here and following the direction of current C, which is downward through this 8 ohm, this will be positive, and this is a voltage drop. Now, and going through this 8 ohm resistance, this will be positive and this will be negative. So what is the net upward current through 8 ohm resistance? Net upward current is IC minus IB. Now we write equation for mesh C. So across the 8 ohm resistance is the right hand side. So this is equal to 8, and only IC is flowing through it. Another voltage drop across this 8 ohm resistance is 8 IC minus IB is equal to 0. Combining coefficient, there is no IA term, only IB and IC. So this is minus 8 IB and IC over here. This is IC and IC, and it is plus 16 IC. Right hand side is equal to 0. And this is our equation 3. Now we have got 3 equations. But note that, look at equation 1. IA is known, and if we substitute IA in equation number 2 and equation number 3, if there is a IA term, the number of equations will be reduced. Look at equation 2. We substitute IA equal to 2. So this is minus 4 multiplied by IA of 2 ampere. So minus 8 plus 20 IB minus 8 IC. This is equal to 0. And this is equal to 20 IB minus 8 IC is equal to 8. And the second equation over here, this second equation, there is no IA term in it, this second equation. So I will write it as minus 8 IB plus 16 IC is equal to 0. And now we have these two equations. These are our two equations. And now I will delete the equation numbers over here previously, just to make it clear, and I will call it, this is equation 1 and this is equation 2. Solving these two equations, it will be 20 IB minus 8 IC minus 8 IB and 16 IC, and this is equal to 8 and 0, and then then IB and IC. We know IA already due to the current source, and this is equal to inverse of 20 minus 8 and 16 multiplied by 8 and 0. So this is 16 and 20, 8 and 8, divide by its determinant, which is 20 multiplied by 16 minus 64. So this is 256, and this is 8 and 0. And this is equal to, I will keep this 256, and this is 16 multiplied by 8, so this is 16 multiplied by 8 plus 8 multiplied by 0, and then second row is 8 multiplied by 8 and 20 multiplied by 0, so this is 8 multiplied by 8, and then IB and IC is, sorry, I haven't calculated it previously, so I have to calculate it by hand. So it is 16 multiplied by 8 divided by 256. So this is 1 by 2, and the next is 8 multiplied by 8 and divided by 256, and this is 1 by 4. It means that IB is 1 by 2 ampere and IC is 1 by 4 ampere. As the sign of the currents we have calculated, the sign is positive, and if we look at the circuit diagram again, this is 8 ohm, and again I will not hesitate in redrawing the circuit again and again. This is 8 ohm and this is 8 ohm, and the current, which was 2 ampere over here, the current over here, the current flowing in this mesh is IA, which is 2 ampere. The current flowing in this mesh is IB, which is 1 by 2 ampere. Look at the sign of IB. If we look at the sign of IB, it is positive. It means that the actual current is flowing in our assumed direction of the current, which was clockwise. So if we see IC, the sign of IC is also positive. Therefore, the actual current at the end of the day, the actual current which is flowing through this mesh have the same direction, and it is 1 by 4 ampere. Now, just a method of rechecking our analysis. This is if we if we say this node over here, and this is another node, and the bottom node, this is bottom node is one node, the bottom node, whole node is just one node over here, just one node over here, we can verify our calculated values over here. How we can verify? We see current flowing to this node is 2 ampere, and current flowing away in the downward direction. Now 2 ampere, this 2 ampere is flowing downward, and this 1 by 2 ampere is flowing upward. So 2 minus 1 by 2 is 3 by 2. So flowing away, so it is 3 by 2 ampere flowing downward. What is this current? This is only IB, 1 by 2 ampere plus 1 by 2 ampere, and if we add these two, right hand side is equal to the left hand side. What is the current flowing in this direction? This current is 1 by 2 ampere, and the current flowing in this direction, net downward current flowing in this direction is IB minus IC. IB is 1 by 2, IC is 1 by 4, so this is 1 by 4 ampere. What is the current flowing? So this is only IC, so this is 1 by 4. So current coming towards the node is 1 by 2 ampere, flowing away from the node is 1 by 4, 1 by 4. So it is verified. We can also see the voltages. We can also see the voltages across each circuit element over here. Now, the current flowing downward, which is IC, and IC is 1 by 4 ampere. Therefore, the polarity of the voltage drop is as shown, and we have 2 volts over here. The net current flowing downward is IB minus IC. So IB is 1 by 2 ampere, IC is 1 by 4 ampere. So the net downward current is 1 by 4 current multiplied by the resistance. Again, the voltage drop is 2 volt. As these two resistors are in parallel, so the voltage across these two should be same. So what is the voltage drop across this with this polarity? Only IB is flowing through this. And what is the voltage drop over here? IB is 1 by 2. So this is 4 ampere over here. What is the net current flowing downward over here? This is IA minus IB. So IA is 2 minus 1 by 2. 3 by 2 ampere current is flowing downward, multiplied by 4. This is 6. So this voltage is 6 volt over here. Now we see if we move around the middle loop or mesh, this is voltage drop 4 ohm, this is voltage drop, this is voltage drop, this is the voltage drop is 4 volt, voltage drop is 2 volt, and this is voltage rise, this is 6. So voltage drop 4 plus 2 must be equal to 6. So we can verify. I wanted to give you a little explanation that whenever you calculate values of currents or voltages, you can verify your answer quickly. Now, moving forward, I will consider another example. I have selected examples carefully to cover all aspects of this mesh analysis. So, another example here. Now, this example is an interesting example in a way that it is different from the previously discussed example. We have resistance and we have a current source over here, and let this current source be IS2, and there is resistance here, this is R3, and let this resistance be R1, and there is another current source over here, current is flowing upward, let this be IS1, and then and the right hand side we have a resistance. This is R4, and that's it over here. Again, listen carefully. We identify all meshes, and we see that number of meshes is equal to 3. And let us call it mesh A, let us call it mesh B, and let us call it mesh C. Special thing in this circuit is that we have a current source shared by two meshes, mesh A and mesh C. There is another current source again shared by two meshes, mesh A and mesh B. If you see our previous example, in this previous example, this 2 ampere current source is shared only by one mesh current. This is a special thing in it, you should remember. And over here now, sorry, I have to rewrite. As this current source is shared by two meshes, IA and IC, I rewrite over here current source, and this is IS2, and I will not show the rest of the circuit over here, rest of the circuit. If we look at this side, IEA is flowing, and if we look at the upper side, so this is IC. Look at the original circuit, IC is clockwise, IC flowing through this is in the direction shown in red. Now, what is now IS2? Look at the direction of the current flowing through this current source and the direction of the mesh currents. So following the directions, the net current flowing from right to left, net current flowing from right to left, I am repeating again and again, this is IC minus IEA. IC is flowing from right to left, IC is flowing from right to left, and IA is flowing from left to right. So the net current flowing in the direction, the net current flowing in the direction of the current source is current is IC minus IA, the difference of these two. I can rewrite this equation as minus IA plus IC is equal to IS2. We can call it equation number 1 here. Now, look at the current source over here, this current source. Look at the original circuit diagram, this current source. As the current source over here, upward direction IS1, and if you see the direction of current flowing in mesh A and the current flowing in mesh B, as this is shared by two meshes, what is the net current flowing upward? IB is flowing upward, IA is flowing downward. So the net current flowing upward is IB minus IA. Therefore, it is very simple. Whenever you see a current source shared by two meshes, it will be very simple to find an equation. So I write IB minus IC is equal to IS1. Okay, it's already arranged in an ordered form. So this is equation number 2. I have written something. Okay, sorry for mistake. It is this is IB minus IA. So it is IB, this should be IA, this should be IA, and I can rewrite this equation as minus IA plus IB is equal to IS1. Now this is a neat and clear equation too. Now, interesting fact in this circuit is that due to the current sources over here, if you look at mesh A, there are two current sources in it, and IS2 is shared by mesh A and C, while IS1 is shared by mesh A and B. Now, if we want to write the mesh equation, we have to move along the direction of the current IA over here. So the path is complete over here. We can find the voltage drop across R1. What is the voltage drop across this R1? So voltage drop across R1 due to the current flowing through it. And what is the current flowing through it? IA. Now, what is the voltage drop here? Here, voltage drop, look at the circuit diagram. What is the voltage drop here? Unfortunately, at this stage, we cannot determine the voltage drop over here because this element, circuit element, is a current source. It is not a resistor. We don't know the resistance of this at this stage, and equivalent resistance are, so we don't know what is the voltage drop. Therefore, we cannot proceed further. We cannot write equation for mesh A. Now, if we see mesh B, we can write, we know the voltage drop, and this voltage drop is what? This is R3 multiplied by R3 multiplied by IB minus IC. Yes, we know the voltage drop over here. So what is this voltage drop? This is R4, only IB is flowing. But what is the voltage drop over here? So we don't know what is the voltage drop over here at this stage. Later, when we will complete our analysis, we will find voltage drop over here. But at this stage, we don't know what is the voltage drop across the current source. Therefore, we cannot proceed further. Now, what we do? Now we write loop equation over here. We will write loop equation, and there is a loop. And the loop over here, if we see, the loop is okay, the color, the outer loop. Start from here. Look at the circuit diagram. If we start from here, this we go through R2, and what is the voltage drop? Voltage drop is the polarity of the voltage drop over here. The voltage drop across R2, what is the current flowing through this, is IC. Now, over here, and then what is the voltage drop here across R4? This is again the voltage drop with the polarity shown over here. Only IB is flowing. And now we go through R1. So what is, and the loop is complete. What is the voltage drop over here across R1? We write voltage drop across R1 due to current IA is equal to 0. Now you see that we have avoided, in this loop we have avoided, in this outer loop over here, we have avoided the current sources which was creating problem. Now I just remove everything from here. Rearrange this equation. The coefficient of IA, I have to write in an ordered form. IA, then IB. This is R4. This is R4. and then IC plus R2 IC, this is equal to 0, and this is our third equation. Now all these equations can be expressed in a matrix form. So this equation over here, minus 1 IA, 0 IB, and 1 IC, 0 for missing elements, is equal to IS2. So if I express it in the matrix form, it is over here. And then the second equation, this is minus 1 IA and 1 IB. There is no IC term, therefore it is 0 over here. And let me check. This is okay. And the right hand side is IS1. Now the third equation over here, R1 IA, R4 IB, R2 IC, and the right hand side is equal to 0. So this is have I written this correctly? Let me recheck it. This is R2 IC, okay, and R4 IB, correct, R1 IA, correct. So this is R1 and R4 and R2. So we can solve it, and over here we can solve it for IA, IB and IC over here. Knowing the values of IA, IS1 and IS2, the current sources, we can, and the resistances are 1, 2, 3, 4, we can solve this matrix equation easily. Now if I'm please verify it by yourself that IA, this is my inverse of this, IA is minus R4 divided by R1 plus R2 and plus R4 IS1, and this is R2 divided by R1 plus R2 plus R3 IS2, and IB is minus R4 divided by R1, R2, R3, this is IS1, and R1 plus R4 divided by R1, R2, R4 IS2, and IC is R1 plus R2 divided by, denominator of every term is same because it is the determinant of this matrix when we computed its inverse. So over here IS1 minus R2 divided by R1 plus R2 plus R3 IS2. Now, very interesting aspect. I will explain it over here. If I write IA as K1, because K1 is the coefficient of IS1, and K1 is minus R4 divided by R1 plus R2 plus R4. This is K1 IS1 plus K2 over here. This is K2, coefficient of IS2 plus K2 IS2. K2 is minus R2 divided by R1 plus R2 plus R3. I think there is a mistake over here. This is 4, this is 4, sorry for that. This is 4 and this is 4. Similarly, IB is let it be K3 IS1 plus say K4 IS2, and IC is equal to K5 IS1 plus K6 IS2 over here. You can check the values of K1, K2, K3, K4. Some coefficients may have same value, like I can see K1 and K3 have same value, like K2 and K6 are same, and K4 and K5 are also same. So interesting aspect over here is that in our circuit we have three sources, and the sources are we have two sources, IS1 and IS2, sorry. So over here, look at the circuit diagram. This is source 1 and source 2. So we have two sources, and look at here, we have IS sources, two sources, IS1 and IS2. IA is scaled sum of these two sources over here. Similarly, IB, it depends on IS1, it depends on IS2. Similarly, IC, it depends on IS1, it depends on IS2. Now, another aspect over here, I redraw the circuit again. And this is R2, IS, this was 2, R3, R4, this is IS1, and this is a resistance R1. Interesting thing in here is, what is IA when IS2 is equal to 0, at least mathematically in this equation. When IS2 is equal to 0, the second term disappears, and this is equal to K1 IS1. Similarly, what is IB when IS2 is equal to 0? In the second equation over here, when IS2 is equal to 0, the second term disappears and it is K3 IS1. Similarly, in third equation, what is IC when IS2 is equal to 0? The second term disappears, so it is K5 IS1. So what is the meaning of this over here? I am saying that when IS2 is equal to 0, in the circuit diagram, when IS2 is equal to 0 over here, it means that I am considering no current over here. The current is 0. For this assumption, I have to remove this current source. If I remove this current source, no current is flowing through this. So then in the resulting circuit, we have only IS1, and we can find IA, IB and IC only due to IS1. Similarly, we can further see that what is IA when IS1 is equal to 0, what is IB when IS1 is equal to 0, and what is IC when IS1 is equal to 0. So what is this? So this is equal to K2 IS2, this is K4 IS2, this is K6 IS2. So it means that, now look at the circuit diagram. I'll place this again over here. IS2 will be over here, and if I want to delete this highlights over here. Now IS10 means I have removed this IS1 from the circuit, and this as well I have removed it. Let's remove, so I will remove it from here. So this is IS1. There is no IS1 and there is no current flowing through this. Now I can find IA only due to IS2, only due to IS2, only due to IS2. Then I can combine IA with both IS1 and IS2. This is known as principle of superposition, and this principle of superposition will be discussed in the next part of the discussion. Now the linearity property of electrical circuits. As you know, we are discussing only resistive circuits. Resistive circuits, all resistances, and we are using voltage sources, ideal voltage source or dependent voltage source, and current sources. This is ideal current source, and this is dependent current source. A circuit which consists of only these elements as shown is known as linear, because the voltage remains fixed across here, the current remains fixed across here. So if this voltage source, if the dependent voltage source, I can express it as say 5 IX. Once IX is fixed, the voltage across this will be 5 times IX. It may be, say for example, it may be 7 Vx. Vx may be some voltage in the circuit across some element, and Ix may be some current. So at one time, in this case, this is a voltage source which is depending on a current variable, and this is a voltage source which depends on a voltage. So this is a dependent voltage source, and similarly the second one, dependent current source, we may have 5 Ix over here. So the coefficient may be any. 5 Ix means the current flowing through this dependent current source is 5 times Ix. What is Ix? Ix is any current in the circuit. Now this dependent current source is depending on a current variable or current signal, and this current may be a current through some circuit element, and this may be say 2.5 Vx. Again, this is a current source, but now the current in this dependent current source depends on is a control variable Vx, which may be the voltage across some circuit element. So when we have fixed resistors and dependent and independent voltage sources and current sources, the circuit is essentially linear. Now again, a simple example. You can see this example in the textbook as well. and in this we have two sources. One is voltage source and other is current source. Both sources are independent sources. The voltage across voltage source remains fixed, whatever is the current flowing through it, and the current through the current source remains fixed, whatever is the voltage across it. So, and this is resistance is R2. This is a very simple circuit. It has nodes and it has three nodes. Now, in this circuit, how many inputs we have? We have two inputs. There is one voltage source and the current source. And we see the output. How many outputs we have? Till now, we have not shown any outputs in it. Now, consider the voltage across R2 as our output variable. We can consider the current through this R2 as output variable. We can consider current through this R1 as output variable, or we can consider voltage across R1 as output variable. So, but I will stick to the example where the output is the voltage across R2 and the number of output is equal to 1. So this is two inputs and one output circuit. Now, in this we can determine VO. How we can determine VO? At this stage we have discussed node voltage analysis and mesh current analysis, and we can apply any method. So let us apply node voltage method. So applying node voltage method, this voltage is Vs with respect to ground, and the second node, this voltage is VO with respect to ground. I am considering the same symbol VO over here because VO appears across R2 and R2 is connected between this node. Look at the circuit diagram, this node and the ground node over here. Now I will write equations quickly. Again, as a practice, I will write equations quickly. Let me insert some space over here. And the voltage at the equation, we need only one equation over here because the voltage at this node is Vs with respect to ground, and it is shown due to this voltage source. Now I write equation only for the node at the right hand side indicated by VO. So this is VO, current flowing away from the node due to our assumptions as discussed in the node voltage method. VO minus Vs divided by R1 and plus current in this through this R2 flowing away from VO. VO minus 0 divided by R2, and the current we will stick to the direction of the current of this current source. So this current is coming towards it. If we simplify it, then VO will be equal to R2. You can do it by yourself. So this is R1 plus R2 and times Vs and plus R1 R2 divided by R1 plus R2 times Is. Now we can say that VO, because the coefficient of this Vs and the coefficient of Is, these two coefficients are constants due to resistances. So we can say this is K1 and plus this is K2. We see that the output voltage is linear sum of the sources, two sources, Vs and Is. Mathematically, we can express it, the output voltage, which is function of x1 and x2. x1 and x2 is shown as input. This is the mathematical form. This is equal to the output due to one source plus the output due to the other source. So don't worry about this mathematical representation, soon it will be clear. So this property of linear circuit is known as superposition. superposition. Now, this superposition, this principle of superposition can be further explained if we consider these two sources one by one. So we see that the output voltage due to this term shows the output part of output voltage, which is only due to Vs, and this shows the output voltage only due to Is. So from here we can see that output voltage when the current source is removed, this is equal to K1 Vs, and the output voltage when the voltage source is removed is equal to K2 Is, and the output voltage due to both of these two sources is shown already over here, This is the output voltage due to both inputs, both sources over here. Now I will redo this again. Okay, there is okay, first I will, light is not getting over here. If you see this, and this was not like that, sorry, I need to insert a space over here, and sorry for this. First I need to insert a space over here. I need space, and now I will take this circuit to this place over here. Now, in order to see what is the output voltage when Is is equal to 0. In this case, when Is is equal to 0, it means that we remove this current source. We remove this current source over here, and over here it is I have removed the current source. Now I will say output voltage VO1 due to source 1, which is the voltage source. I have eliminated the current source. It is very simple to find VO1 only due to Vs, due to voltage division rule. This is equal to R2 divided by R1 plus R2 and Vs1. And you see that this part of the output only due to Vs is already shown over here. Only due to Vs is already shown above. Now I need to, sorry for that. And now I see the output only due to the output when Vs is equal to 0. What is the output when Vs is equal to 0? Now, doing so, I have to remove this voltage source. So if I remove the voltage source, means Vs0 So Vs appears, as you know, Vs appears across these two nodes, the bottom node and the top node. In order to make Vs 0, I have to short circuit this. So the voltage is 0. So when we remove a voltage source, we short circuit its two terminals from where we have removed, and when we remove a current source, we open circuit. Now in here we see that it is we can easily apply current division rule, and let me use different symbol over. This is VO2, means only due to the second source, output voltage only due to second source. Now I can differentiate, this is VO2 and this is VO1. Now we see that current over here flowing in this direction and flowing in this direction. Due to current rule, you should know due to chapter 2, I have already discussed chapter 2. So due to current division rule, the voltage is equal to R1 divided by R1 plus R2 multiplied by, I will use the same thing over here, IS. So this is the output voltage due to IS. I have to multiply over here. So this is the voltage. In fact, without this R2, this is the current flowing through the R2, and if I multiply the current by R2, this will be the voltage. And now over here you can see now this is the output voltage due to Vs, and when we considered it individually and see above in here, this is the output voltage due to Vs, and the output voltage due to Is over here, and the output voltage due to Is over here. Now in here, in this expression, we considered both sources, and we applied node voltage method in order to find the overall VO due to current source and due to the voltage source. Over here we have found output voltage only due to Vs and output voltage only due to Is. And now finally we can say that output voltage, net output voltage, is sum of these two parts. Note that this is the output voltage due to voltage source only, and this is the output voltage due to current source only, and we add these two and it is equal to R2 divided by R1 plus R2 and Vs1 and plus R1 and R2 divided by R1 R2, and this is Is, and you can see it, you can compare it with the previous example. Now if I say output is Y and this coefficient is K1 and this voltage source is represented as X1, and then this coefficient is equal to K2 and the second source is represented as X2 over here. So Y is scaled sum of the both inputs. We can express it in a figure, we can express it graphically. Engineers, they prefer block diagram representation. So we can say that we have source X1, we have source X2. We are using just labels, letter symbols for X1 representing the voltage source and X2 representing the current source, and X1 multiplied by K1. K1 is a proportionality constant determined due to resistors in the circuit, and K2 is another proportionality constant. which is R1 R2 divided by R1 plus R2, and we multiply these two. So this one is K1x1 and this is K2x2. In this method, the output will be equal to the input multiplied by the gain shown in the block over here. And now we can express this equation in the form of block diagram: K1x1 with a plus sign and K2x2 with a plus sign over here, and output is equal to Y. So this is principle of superposition. Now in here, I discussed this example in my previous discussion, and again I think it is the same example. Right, this example is with values. It is I use the values, okay, 3 ohm, 9 ohm and 6 ohm, and here you see what is IA, IB. I have taken this example from the previous discussion. So this is IA and this is IB over here. And if we assume in here, in this circuit, we can assume that our output variable is VO. VO is the voltage across this 6 ohm. Now this VO, if we express VO, then VO will be equal to, what is VO? In the indicated direction. So VO is equal to 6 ohm multiplied by IB minus IA, and we see that it is 6 ohm multiplied by IB minus IA. This is IB, and it is 6 over 99 VS1 minus 9 over 99 VS2, and minus IA, this is minus IA, it is 15 over 99 VS1. Due to minus, this will be plus 6 over 11 VS2 over here. And now we can proceed further. This is again to save time. We see that we have VS1, we have VS1, we have VS2, and we have VS2. There will be some coefficient of VS1 and there will be coefficient of VS2. And we can see that due to this equation, we can express as VS1 in the form of block diagram: VS1 multiplied by K1 and VS2 multiplied by K2. We add these two, signs are plus over here, and this is VO. This is the block diagram representation. And what is VO when source 1 is 0? From this equation, this is K2 VS2. And what is VO when VS2 is equal to 0? So from the same equation, it is K1 VS1. Doing so, we can again see the circuit over here. If we take the circuit again, put it over here. For this, in order to find output voltage only due to VS2, we have to eliminate this voltage source. How we remove a voltage source? Removing voltage source means we short circuit, we delete the symbol on paper, we delete the symbol and we short circuit. Now VS1 is 0 because VS1 was between these two nodes, the ground node and the node shown over here. VS1 is equal to 0. So the output over here is only due to VS2 over here. And next, for this, when Vs2 is equal to 0, for Vs2 equal to 0, we have to eliminate this Vs2. So Vs2 is 0. There's no harm if I write Vs2 is equal to 0, means now the voltage which was over here due to short circuit, the voltage is 0 now, and we have to put this source again, source 1 Vs1 over here. ये इसको दोबारा यहाँ पे मैं रखूँगा over here. So this is Vs1, and now if you solve this circuit, you will find that output voltage due to Vs1, due to left hand side voltage source, is equal to this. And let us use proper labels over here. So in here, this is only due to voltage source 2, and this output is only due to Vs1. Then we say that the net output is equal to VO1 plus VO2, and you can verify it. This is principle of superposition. Now let us see over here. This is another example, and in this example we see that we have two sources. This is IS2 and this is IS1. If we solve this circuit for say, I remember perhaps it was IA, and if I remember this was IB and this was IC, see the lecture above. So this is IA due to IS1 only, and IA due to IS2 only, and similarly it is IB, it is IC over here. So in this circuit, where is output? We can mention, we can show the output, say over here. Usually in the textbook you will see the output is shown on the right hand side. So this is VO, and I will write VO is equal to R4 multiplied by R4 multiplied by only IB is flowing through it, IB. Now this can be expressed as K1 IS1 plus K2 IS2. This is IB. So this part of output voltage is only due to IS1. This part of output voltage is only due to IS2. You can use principle of superposition. In order to find this part only due to IS1, you have to eliminate the second source. Over here, eliminate IS2 means open circuit the IS2 source, and solve the circuit for VO. And in order to find the voltage, output voltage only due to IS2, eliminate this, and you can find the output voltage only due to the second source. The net output voltage will be sum of these two. This is principle of superposition. So the discussion can be extended to further examples, but I think this is enough. So this is end of lecture 2. Thank you very much.